So this is a question related to the design of a tension member to carry a factored tensile load of 200 kilonewton, and the length of the member is given as 4 meter, and the tension member is to be connected to a 16 thick gusset plate using 20 diameter bolt of grade 4.6, and we have to use single angle sections. So the question itself, the factored load is given as 200 kilonewton, and to resist this factored load we have to select a member, and we have to check for the failures in a tension member, which are gross section yielding, net section rupture, and block shear. So here in section 6 of our IS 800, which is in page 32, there we have given in 6.1 itself, the member shall be satisfying the requirement of T, which is the load which is given, and that has to be equal to our design strength of the tension member. Now the first step is to find the gross area. So both in tension and compression member, the area will be the deciding factor. So the gross area AG has to be computed. So when we look at clause 6.2 in page number 32 of IS 800, it is given as the design strength due to yielding of a cross section. There TDG, which is the gross yielding, is given as Ag times Fi divided by gamma m0. So here Ag denotes the gross area, Fi is the yield stress of the material, and gamma m0 is the partial factor of safety of a tension by yielding. Now Fi we always know we are providing as 250 Newton per mm square. This is the Fi value. And gamma m0 is the material strength of steel. And if you look at table 5 of your IS 800, which is in page number 30, it is 1.1. And we have taken the factored load equal to our total design strength due to yielding. So using this equation we can calculate the gross area required. So substituting the values of TDG as 200 kilonewton, which is in Newton it will be 200 into 10 raised to 3 multiplied by our factor of safety 1.1 divided by 250, we will be getting the gross area required as 880 millimeter cube. So we have to select an angle section such that it is having an area greater than this value, and this will be able to resist the factor tensile load of 200. So usually the angle sections are given in IS 808. So when you go to IS 808 and in page number 8 is given the equal angle sections, and if we look at angle 80 by 80 by 6, it is having a sectional area of 9.29 centimeter square, which is equal to 929 millimeter square. It is greater than 880. So, and it is also having a Cx value. Here we can see this is our Cx value, this distance. So usually at the centroid level only we will be placing our bolted connection. So in this question it is given to design as a bolted connection. So these values has to be noted. The Cx value has to be noted because this is the distance actually we will be placing the bolt from the bottom. The sectional area will be 929, which is greater than 8.8. Thus from IS 808 in page number 8, we have selected the angle as ISA 80 by 80 by 6 mm having a gross area of 929 millimeter square, and this is greater than the required area, which is 880. Now what we have to do, since we have to design a bolted connection as a connection joint, we have to find the number of joints, the number of bolts. So then only we can do the remaining design checks, that is in rupture check and the block shear check. Now here the load is given as 200 kilonewton, and for that load we have to design the connection. So our next step is to find the number of bolt, E which is the end distance, and P which is the pitch distance. So here in the question itself, the nominal diameter of the bolt is given as 20 mm. And we know that if the diameter of the bolt is given, the diameter of the bolt hole D0 will be 20 plus 2, which is 22. And this value is obtained from table 19 of our IS 800, which is in page 73, where we look from 16 to 22 for standard bolt size are 2 mm. Now also in the question, the grade of the bolt is given as 4.6. From this we can calculate the ultimate strength of the bolt, which is denoted as FUB, and this will be equal to 4 into 100, which is 400 Newton per millimeter square. Now here Fe 410 grade plate is not given as the gusset plate, so we can assume the gusset plate to be having Fe 410 grade, so its ultimate value will be 410 and the yield value of the plate will be 250 Newton per millimeter square. Now if you look at in the design of connection, which is in chapter 10 of our IS 800, and as per the clause 10.3.2, the design strength of a single bolt, which is denoted as VDB, must be taken as the smaller value of VDSB, which is the shear capacity of a bolt, and the VDPB, which is the bearing capacity. Now we will be calculating the shear capacity of a bolt and bearing capacity of bolt, and the smaller value will give you the design strength. And to find the number of bolts, we have to take the ratio of total factor load, which is 200 kN, divided by our design strength of a single bolt. Now in clause 10.3.3 in page 75 of our IS 800, the shear capacity of bolt is given, and this equation is given as VDSB is equal to VNSB by gamma NB, where VNSB equation is FUB divided by root 3 into NN ANB plus NS ANB. So all the nomenclatures are here. NN is the shear plane in thread area, ANB is the area of threaded area, NS is a shank area, ASB is the area of this shank area. So the bolt will be having a thread area and a shank area. So since we are designing for a single angle connections to a gusset plate, the number of shear planes. So here if this is the gusset plate and if this is the angle which is to be connected, the shear plane will be 1 only. Hence if we consider Nn is equal to 1, the Ns value will be 0. And for thread area, the area has to be multiplied by 0.78 times the nominal area of the bolt, which is 20 mm bolt. It will be pi by 4 20 square. Why we are applying 0.78 is for threaded areas the area will be lesser, so to accommodate that we are compared to the shank area, that's why we are multiplying it 0.78. So since Nn and Anb are considered and a single shear plane is there, the Ns will be 0 and ASB will be 0. Now our equation of VNSB will be substituting the ultimate strength of the bolt, which we have found earlier as 400 divided by root 3 multiplied by Nn into Nb. This will be 0. So while substituting, we will be getting a value of 56,594.18 Newton. This will be Newton. Now we will take this value, and in the clause 10.3.3 it is given as VDSB will be the VNSB, the nominal strength, design strength will be nominal strength divided by the factor. By substituting, I obtained the value of VDSB for shear capacity of the bolt as 45,275.35 or 45.275 kilonewton. Now it is already given in the clause that we have to also find the bearing capacity, and out of this a smaller will be considered as the design strength of the bolt. Now the bearing capacity is given in the next clause of our section 10, which is clause 10.3.4, and the page number is 75 of our IS code. And these are the equation. Design bearing capacity of a bolt will be nominal bearing capacity divided by the factor of safety of the bearing type bolt, and the nominal value will be 2.5 times the kb, which is a constant, into d, which is the nominal diameter of the bolt, multiplied by the thickness of the plate, multiplied by fu, which is the ultimate strength of the plate. So all these nomenclatures or the extension is given in the code itself. So here d, we already know it is given in the question as 20 diameter bolt. So this will be taken as d, and t is the thickness of the thinner member. Since the cassette plate is having a thickness of 16 and the angle thickness we assumed it is 80 by 80 by 6, where 80 by 80 it denotes the leg sizes and 6 denotes the thickness. Now what will be the t value? The minimum of 16 and 6 will be 6 Now the ultimate strength of the plate, if we are assuming a Fe 14 grade, the strength will be 14 Newton per millimeter square. To find the kb value, we have to calculate the E and P value. So E is the end distance, P is the pitch. Now if we look at clause 10.2.4.2, the end distance for a machine cut type bearing bolts has to be 1.5 times the diameter of the hole. So we already calculated the diameter of the hole. So the 1.5 and 22 gives us 33. Now we will round up to 35. We take this value as the end distance. Now the pitch distance is given in clause 10.2.2, which denotes the minimum spacing between the fasteners. That is basically means pitch. And this will be equal to 2.5 times the nominal diameter of the fastener, which is in this case the fastener is our bearing type bolt. So it will be 2.5 20, it will be 50 Now the kb will be the smaller of E by 3d0, which is given in the code, or P by 3d0 minus 0.25 and Fu by Fu, and this has not been considered because majority cases these two will be the smaller values. The E is 35, 3 times d0 is the diameter of the bolt hole, and P is the pitch distance. When substituting, we will be getting 0.53 and 0.507, and the smaller value will be 0.507, and we will be considering this as a value for kb. Now we will be substituting everything back to our nominal bearing capacity of the bolt, 2.5 into kb, which is 0.507. The nominal diameter of the bolt will be 20, and 6 is our minimum plate thickness multiplied by our ultimate strength of the plate, 400, and I am getting an answer of 62,361 divided by the factor of safety of the bearing type bolt, which is 1.25, and all this gamma mp, gamma m0 and gamma m1 can be obtained from table 5. We are using a bolted connection, and in section 10 itself we are studying about bearing type connection. So gamma nb will be the factor of safety for the bearing type of joint. So this will be solved as 49.8 kilonewton. So always the values will be in newtons, so will be converted into kilonewton. So what is the design strength of the boat? VSB. This will be equal to VDB. Now we already has discussed about that clause in which we have to take the minimum of the design strength due to shear and bearing. So while considering these two values, 45, which is the shear capacity bolt, will be the minimum value. The number of bolt is given by the total factor load divided by this design strength of the bolt. So the factor load is given as 200 kilonewton, distance is 45. By solving, we're getting 4.41 as the number of bolts. So we'll be providing 5 number of bolts for supporting the single angle to the cassette plate. Now we have calculated the section size from the steel table, which is ISA 80 by 6. We also calculated the number of bolts. So when we see, the figure will be looking like this. Now what we have to do, we have to check for the whether the tension member we considered and whether the bolt sizes we provided are safe or not. Now we go to the section 6, page number 32. We can see that already it is given under the clause 6.1 that the design strength of a member under axial tension, which is TD, is the lowest of the design strength due to yielding, which is TDG, due to rupture strength of critical strength as TDN, and due to shear lag as TDB. So all this value will give you a design strength, and if this value is greater than the factored load which is applied, which is 200, then our tension member will be safe. So first is gross section yielding, which is given in clause 6.2 of page number 32, and the equation is TdG is equal to AgFy by gamma m0, where Ag is the gross area of the I section that we have considered. Fi is the yield strength and gamma m0 is the factor of safety for the material. So Fi is considered as 250, and gamma m0 can be obtained from table 1, which is table 5, which is 1.1. Now when we substitute where this value of Ag, which is the gross area of 80 by 80 by 6 mm angle, it is obtained from IS 808 page number 8. It is 9.29 centimeters square, which is 929. So all this we have discussed earlier also. I'll be getting a value of 211, and this is obviously greater than our considered factored load. So this angle section will be safe in gross yielding. Net is to find the rupture strength. Now 6.3 will of the section 6 of page number 32 is dealing with rupture strength, but for single angle section we have to see clause 6.3.3 in page number 33. So this will be talking about the rupture sum of a angle connected to one leg. So here only one leg will be connected to our gusset plate. This is the leg, and the bolt will be provided along the centroid of the angle section which we consider. And this value of Cx is obtained from IS 808 itself. It is given. Cx, Cy values are given. And now this is the equation which is given in your IS code. You have to write this equation as such, and this explanation of each term is given below. What is ANC? ANC is the net area of the connected leg. Here both legs are having 80 mm as the size, and this leg will be connected. Now this leg connected will be having a bolt hole, so we have to reduce that area while considering the net area of the cross section of the angle which is connected to the bolt hole. Now the small areas thickness will be overlapping, so we will be reducing that from our equation. So LC is the length of the connector, which is 80, n times dh. If there are two bolt holes, we have to reduce that also. Since here is only one, n value will be 1. So the net area of the connected angle will be the total length, which is 80, minus the bolt hole diameter, which is only 1, and it is given in a row. So every time we cut a section, we will be seeing only one bolt along that section. So that 1 into 22 minus, we have to reduce half of thickness. And what is the thickness of the angle section overall? It is 6 mm. So when we calculate this, we'll be getting the net area of connected members as 330 millimeters square. Now what about our ultimate value Fu? This will be the strength of the plate, which is 410 MPa or Newton per millimeter square. If somebody is returning MPa, it is same as Newton per millimeter square. So I'll be changing this to Newton per millimeter square. Now what is gamma m1? It is a factor of safety of the bolt in bearing, which is 1.25. Next thing we will be discussing is regarding the beta value. Now here a beta is the value which takes the effect of the shear lag. So usually beta will be called as a shear lag factor. Now the beta's equation is given below the equation of TDN in the IS code under the clause 6.3.3 in page 33, and this is the equation, that is 1.4 minus 0.076 multiplied by W by T into Fy by Fu into Bs by Lc. So all these things has to be considered as a single, then we can reduce from 1.4. Now W, all this value is given in figure 6 in the same page number 33 of IS 800. So W is the length of the outstanding length. So the outstanding length is 80, which you can provide as such, and T is the thickness, which is 6 mm for this angle, and we know the value of Fy, which is the yield strength, and this value is 250, and we know the value of Fu, which is ultimate strength, and this value is 410. Now the Bs, and this definition of Bs given in the code is the shear lag width. Now we know shear lag, it is unbalanced shear developed due to the outstanding leg of an angle section. So it will be mostly asked in theory part. Now the shear lag distance, when we look at here in this figure, the distance from this end towards this end. So we have to add the W value, right? The length of the outside leg plus we have to add the distance between these 2 points, which is 21.8, minus this is an overlapping thickness in both sides, so I have to minus the sum of t by 2, which is t only. So using that can find the value of bs, which is 80, which is the width of outline. W1 is the distance from the base towards the centroid minus 6, and this value will be 95.8, and this will be the total shear lag length. So this has to be used in our beta calculator. Now next term associated which is called as LC, and this is the distance between the outermost bolt. Suppose I have provided 1 2 3 4 5 number of bolts, so LC will be the distance between outermost bolts, and the measurements of bolts are usually conducted along the center of the bolt. So we can see there are 5 numbers of bolt, means the distance between the outermost bolt, this bolt distance will give you the value of LC. So this is basically the length of the connections. So in our question, we have calculated the pitch distance as 50, end distance as 35. So if there are 5 bolts, this in between there will be 4 spacing, 1, 2, 3, 4. So the total end to end LC value will be 4 times 50, which will be 200. Now substitute all these values in our beta equation, which is just written here. W will be 80, T will be 6, and all we will be getting a value of 1.104. And we can also do a check whether this beta value is less than fy by gamma x over fy by gamma in 1, which is given in clause 6.3.3, which is always 1.4, and also this value must be greater than 0.7. So our 1.1 satisfies both this. It falls between 1.44 and 0.7, hence it is safe. Now the next term associated with our net area calculation is AG0. So G means gross, O means outstanding leg. So we know the width as 80 minus the thickness 6 by 2 into 6, we will be getting 462. Gamma m0 value we know. All these things will be substituted in the rupture strength of single angle, and we will be getting a value of 213.336 kilonewton, and this is greater than our factor load of 200. Hence our angle section 80 by 80 by 6 will be safe under net rupture strength. Now this is the value which we obtained in Newton, because we have everything converted in Newton, and we'll be taking 3 places from the left will give you, that is divided by 1000 will give you the value of rupture strength. And the next one, which is the last check for the failure of tension member, is the check for block shear. And this is the next clause, which is clause 6.4, and it is given in page number 33 itself of our IS code. So basically block shear is a failure in which a piece of angle section will be failed as a block. So as we can see from this figure, this is the area in which block shear occurs. Always along the bolt hole only block shear occurs. So this is one bolt hole, this is another bolt hole. So along this line the block shear will occurring, and the equation which is given in the code for checking the block shear is these two equations. So the plane AB, and this is the load which is being applied, sorry, the load will be applied is a tension load, and this is applied along the centroid member, okay, along this line, so that there will be no eccentricity or moment, only pure tension is developed. Now we can see this AB plane is parallel to the force, and this will be our shear, okay, this will be our shear area, and BC is basically, this is perpendicular to the load perpendicular, so this will be our tension phase. Now either this area can yield, so once the gross area yields, the net area will be rupturing. So that's why we will considering two equations for block shear, in which one will be weak in shear, other will be weak in tension, like that. So the two combinations, this equation is given, which I mentioned in page 33 under the design strength due to block shear 6.4. Now we will be calculating each area. So the gross shear area, so anything gross area means we will be considering an area without the bolt holes, and the net area AVN or ATN means we are considering the bolt holes. Here we can see this is a 5 bolts, this is 1 2 3 4, and fifth bolt only half will be acting, the remaining half will be returning back. So we have to take the area in this manner, because this is where the failure occurs and this piece will be getting separated, and this denotes the thickness. So basically this denotes the thickness 6 mm. Now gross area will be what? For shear, this is the AB will be the surface. Without any type of bolt holes, we can calculate the total area. So we know that the LC value, the end-to-end distance outermost is 200, and this is the edge distance is 35. So total length will be 235 and the thickness is 6 mm, because we are using a 6 mm angle section, so that has to be multiplied. So basically the shading portion will be the area which is subject to tension, and this is the shading portion where the shear occurs. Now AVN is the net area due to shear. So net area means we have to reduce the number of bolt holes. Now here when we count the bolt hole, it is 1, 2, 3, 4 and plus a half bolt which is 0.5. So and each bolt hole is having a measurement of 22 millimeter. So the net area will be the total length, which is 200 plus 235 minus 4.5 times the bolt hole, multiplied by the thickness, which is 6. Then only we will be getting the net area. Now the next term will be ATG. So it is the gross area and tension. T denotes tension, G denotes gross area. So this length is 58.2. How we obtained? We already know the length from the bottom to a center is 21.8, which we obtained from IS 808. Now the total height will be 80. So 80 minus 21 will give you this length, which is 58.2. And this area will be under tension. The gross area will be that multiplied by the thickness of the angle section, which is 6 mm. And now in the net area we have to reduce the bolt hole. Only half of the bolt hole will be remaining, that is in BC space, 0.5 only. So that we have to reduce from the 58.2 multiplied by the thickness will give you the net area. So I am again repeating, gross area won't consider any kind of bolts, but net area will consider the bolt holes, because the net area is the area where rupturing occurs. So it will be occurring along these holes, bolt holes. Now we will be substituting the value in TD by 1, AVG, which is 1010, Fy is 250, root 3 gamma is 1.1, 0.9 into ATN, so ATN is 232, and we'll be getting a value of 268.6, which is greater than our design load which is given in the question, factor load, which is 200. So in this TD1 and TDB, the minimum will be considered as the block shear strength, and here 0.9 AVN is the net area of shear, Fu is 410, and divided by root 3 into gamma n1 4 bolts, which is 1.25. Now what is ATG? It is the gross area and tension, which is calculated here. Fi is yield multiplied by 250, which is the yield strength, divided by 1.1, which is a factor of safety. We will be solving, and the minimum value is 280, which is greater than 200 kN. Hence our design section assumed, that is the angle section 80 by 80 by 6 is safe for these design checks. I am again repeating, the design checks are yielding, rupture and block shear.